And good morning, folks. How are we doing today? We get all set up here. Doing all right? Doing all right? Oh, we can't hear me. Sorry. Zoom can't hear me. Hello, good morning. Got to unmute. One of the tricks of the trade. You got to unmute your mic to make it work. All right. How are we doing this morning? All right. Some thumbs up, I see. Wonderful. Wonderful. Just to make sure everyone can hear. All right. So we're going to follow up on what we covered last week with single shooting trajectory optimization, okay, where we are trying to apply optimization to control. So right now is a good time if you're in the class. If you need to follow up on the code that we did last Thursday, it is up on the Canvas page. Go to the Canvas page, go to the files page, and then there under tutorial code, you will see all the code from last lecture. If you weren't following along or if something didn't work, you can go download that now, and I recommend doing that right now. Put it in a new folder. We're going to edit it. It's going to be fun because we're going to build off of what we did before. Okay, so just as a reminder, let me pull up what that code looks like. So right here, we were covering something called trajectory optimization, single shooting trajectory optimization, where we had this particular script that we wrote called drag race. We were doing a literal car drag race and trying to come up with the optimal way to have a car start at one position and stop at another position in minimum time, subject to the fact that you can only accelerate so fast and decelerate so fast. So obviously it's going to go, jam on the gas and then jam on the brakes. Okay. And so we got this working right at the very end of class. And so this is what it looks like when you run the drag race.m with all of the, excuse me here, first time, here we go. We run drag race.m as we had it before, okay? And it's setting up an optimization where it's trying to minimize the amount of time it takes. And it tells me once it's all done, it's iterated through. Look at all these iterations here. Iteration. It's searching. What's the best way? What is it doing? It is minimizing here in this column the cost function. You can see it says right here, f of x, minimizing your cost function. And here is how close it is to a minimum. The closer that is to 0, the better. Okay, and it's trying to minimize the deviation from the constraint violation. So the closer that is to 0, the better. So it's 10 to the minus 6. Okay, so yeah, we got that. So then it solves. It says, "Hey, local minimum found. We found one. That's good. And it is not guaranteed it will find it. You can set up a problem poorly, and it might not find the answer. But here it tells you, I found the answer. It says local minimum found means it finds the minimum of the cost, satisfies the constraints, and then we spit out the answer. It looks something like this, and we just said, hey, what? And these are all the different force points over time. It's saying, jam on the gas, plus 10, plus 10, plus 10, plus 10. Then jam on the brakes, minus 10, minus 10, minus 10, minus 10, etc. Okay? Let's plot what these trajectories look like, okay? So right now, sorry, we'll plot those later. But that's what you should be seeing when you run your code, okay? So pull that up when you can, and let's go over to the board in the meantime, all right? So we have today, we're going to cover more trajectory optimization because there are lots of ways to do trajectory optimizations. And this is a really simple one. And one which we can use this very simple approach that we call single shooting. And it works really well for simple problems and sometimes more complicated problems too. Okay. But it's the most intuitive approach. So let's continue where we left off. So today, oh my goodness, what's going on here? I think I might have, no, just need to connect my pencil. My little iPad pencil wasn't working. I'm like, is it out of batteries? That'd be devastating. We'd be miming the whole lecture, or God forbid, we have to use the actual whiteboard over there. That'd be old school for me. So, what do we got here? 2026 02 26. All right. So we're going to continue trajectory optimization. So trajectory optimization. Continued. And we're going to try to do today something called multiple shooting. So this is the method we're going to implement today if we use our time appropriately. Okay. Second. Okay. Multiple shooting. So recall our drag race problem. Okay, where we had, here's our car, this beautiful car, this rectangular vehicle that's going to move from one position across the ground to another, right? We want to get there, we want to stop there, and we have some amount of force that we can change over time, F of t. I believe we call U of t, and sorry, we called it U of t in the problem before. Okay, that's a force we can apply to the car. And we wanted to get it to stop there, right? So the way we set this up was as an optimization problem, okay? Where we have some optimal set of decisions, okay? It's going to be subject, is going to be minimum, or it's going to be, we're going to find the decisions that minimize some cost, okay? And we'll call that J of W today. It's been F of W in the past because there's multiple F's. We're changing it to J. We want to find the decision that minimizes that cost. In this case, it's going to be a minimum time problem. And subject to, or such that it obeys certain constraints. So some constraints, we'll call them G of W is less than or equal to 0. Now, as we all know, these are inequality constraints. You can turn, if you have any equality constraints, never fear. You can always put it into this form, as we talked about in the past, just by making two inequality constraints that are in opposite directions. Or in a lot of this software that we're covering, we can actually put in equality constraints exactly, where some GEQ of your decisions must be equal 0, okay? And what we said was, hey, friends, this cost, that was going to be our minimum time. Okay. And here, these are our constraints. And they were things like our final position, and final velocity, you know, being we got to end right here and we got to come to rest. Okay. And also we had limits on U of t. We have only so much acceleration and deceleration that we can do, right? Okay. So part of the trick, what makes trajectory optimization tricky, is that getting this constraint, knowing whether or not you have satisfied it, requires that you simulate, hey, how far did the car go? Did the car come to a stop? So some part of the optimization problem, be it the constraints or the cost function here, requires simulation, right? So, and this was what we call, and the approach we took was called single shooting. Single shooting requires simulating an entire trajectory to evaluate the cost and or constraints. And if you're looking for the required text, that's all linked up on the suggested reading. In case you're curious about any of this stuff, again, this is all up on the Canvas page, but the Rao 2009 survey paper It's all linked PDF on the Canvas page. You can go to the files page and look at that. Anil Rao, he's actually a faculty member at University of Florida down the street, about 2 hours down the street. And he wrote this beautiful paper surveying all the different types of trajectory optimizations. Okay. So what we're looking at are what we call direct methods. Direct methods. So if you want to read more, I like my explanation. I think it's great for the class, but many people learn differently. So Rao's explanation is quite good as well. I love it. Okay. So signal shooting requires simulating the entire trajectory to determine whether or not the constraints are violated or the cost is minimized, right? See and that's what we have here, right? In order to know the final position, final velocity, we got to simulate. It's called single shooting because you start it because you take a single shot through time, and this is your state, x of t, that's your state, right? That's time. And then this is your trajectory, simulated trajectory. Okay. And you do it once. Okay, and you go across the entire time span. Okay, some final time, capital T. And you might say, my goodness, how that makes sense, right? If you want to know if it worked or not, you simulate it. What else could there possibly be? And we talked about this a couple lectures ago. There are other approaches, and they are wild, and that's one of which is multiple shooting. We'll cover today. But first off, why would you want to do this? Okay, and we talked a bit, again, we want to review from a previous lecture, just as a reminder. So single shooting, so let's talk about single shooting. Some characteristics of single shooting, okay? One of which, okay, is it is not, see, it's less effective for unstable or underactuated systems. Okay? Okay. Stable, we talked about stability in the context of linear systems. You can check the eigenvalues. If you have a pendulum that's face up, right? That's unstable versus face down. Okay, that's neutrally stable or perhaps actually stable, right? And underactuated systems in particular. What do I mean by underactuated? All right, there's an entire course I've recommended in the past by Russ Tedrake that you can look online. And basically, it more or less means that if your system has a certain number of degrees of freedom, you only have an underactuated system has fewer control inputs than you have degrees of freedom. For instance, I have this little object right here I have in front of me here. Let's pull it up here. All right, this little object. All right, and it can move, let's just say in this plane, up, down, left, right. Okay, but let's say I only have a force that I can apply up or down, right? I don't have the ability to push left or right. Okay, that means if I threw it, and I could like put a little thruster on here. Let's put a little thruster on here. We throw a little thruster on here. I can help move it up and down, but there's nothing I can do about its motion left or right. Okay, that would be an underactuated system. Okay, that's a sort of an abstract example. Let's talk about a more concrete example. Let's say walking and running. Walking on legs. Okay. When you are walking, you have a whole bunch of muscles. Okay. So you have a foot that's on the ground that can really help control your whole body to make sure that you can help come to a stop. You stop falling forward. And you are most likely fully actuated when you are walking. You might actually arguably be over-actuated because you have so many different muscles, right? Okay. But when you run, okay, people talk about running as being when you come in, when you launch into the air. Okay, I'm sorry, I'm going to go off on a tangent. There are many definitions of running as a guy who works in legged locomotion. So the colloquial definition of running is that when your legs come off the ground, you're in the air for some period of time. But when you're in the air, okay, even if it's for a brief period of time, there is nothing you can do with your muscles that will change the trajectory of your center of mass, because you are not getting forces from the ground to redirect your trajectories. You are, in a sense, out of control. Yeah, so you can move your arms around, but like you can't, that does not change your center of mass trajectory unless you're like using like air drag resistance, right? It's just like if you're in space, you cannot, if you're in outer space, there's nothing you can do by flapping your arms that'll make you move forward or backwards. You can rotate, but your center of mass doesn't move. That's just Newtonian mechanics. So you are under-actuated when you are in the air, okay? So a lot of times it's useful to have multiple, so single shooting can be worse. Single shooting can be worse. Excuse me. For those kinds of systems. Why? We'll try to give you an example based upon what we've coded already. Okay. Less effective for unstable or underactuated systems. Okay. It does have fewer decision variables and constraints than other methods. Okay, and let's just put up at the top single shooting. These are what we call trajectory optimization formulations. Okay, example of a formulation is single shooting. Okay, so there are fewer decision variables, meaning that your decision vector, at a minimum, only needs your control inputs. Okay, at a minimum, you only need to define control inputs along the trajectory. Okay? And you might recall this from last lecture, okay? Because what we defined from this was our decision vector. Here's our example from the drag race problem. Here's our decision vector. It had in it a bunch of force points, F1, F2, up through Fn, or maybe it was Un, okay? Transpose, because it was a column vector, right? And those were our control inputs, right? So that was, T and U of T. And we defined it as what we call the spline, right? Where we had all these points, and that was like F2, that's F3. The decision vector, those are decision variables. It only requires you have the input in there, okay? We also had a final time TF in there. I know we had that in the previous, but that was helpful in defining what the whole curve was, right? What we will need for these these other approaches is we will also add more decision variables. And that's going to be a little wild and crazy, okay? And they're going to require that we add not just the control inputs U of T, but the states X of T, which again is a little counterintuitive. All right, stop me at any point, because this is actually one of the more tricky parts of understanding material for the course. All right. Okay. Moving on. So now why? So let's go back to our code. Actually, this will be a fun time to go back to the code. All right. So is everyone able to get the code off the Canvas page if you didn't already? Are people to get that? Hopefully it runs on your version of MATLAB. It should be pretty cross-compatible across a couple versions of MATLAB, so it should be good. Is anyone able to run it? Get roughly what I've got here? Anybody? Give me a thumbs up if anyone can run this. Good. Okay, at least one person can run it. Awesome. So when we run this here, that's what we see. It's a deterministic piece of code, meaning there's no random variables determining how the optimization works. So you get basically the same solution every time. There's possible differences between your computer and my computer. But it should be the same time when you run it in the same version of MATLAB and you run it multiple times on your computer, it should give you the same answer each time. For instance, but my computer to your computer might have slightly different numbers. But you can see it's mostly the right answer we got last time, which was, let me pull this up again. You know, we had this. We knew that the right answer to the problem was what we call a bang bang controller, where you got this here, where it's on and then it's off. Bang bang. So bang on, bang off. That's what it's called. Okay. All right. So let's plot this real quick. Okay. So what we're going to do is so we have our solution W star here. So you got a semicolon. Sorry, wrong button. A little rusty. Okay. W star, that is our optimal solution. So what we want to do is let's plot our control input trajectory, keeping in mind that the first n values are our force points. And this last value here was our time duration. Okay. So if we want to come up with our force points, we'll call it our force. So our force points. So we'll call it our force vector. Okay. That's been optimized. Okay. It's going to be the first n values of W star. Okay. So W star 1:n. N was the number of points along the spline that we defined, right? Okay. And we need to know the time points for all of those forces, right? Which they are evenly spaced, as you'll recall. We just evenly spaced them between 0 time and time capital T final, little TF, right? So if we want to get, if it's just a linear spaced set of points, we will use linspace to just generate it. So we would say our time points is equal to a linspace, LIN space, from 0 to our final time. And again, our final time is going to be the last value in our W star. Right here, it says 0.63 is as fast as we can go. Excuse me. So W star, that's our very last one. So it's W star open end. And how many points in the middle? N of them. Okay. So what we're going to do is we're going to plot our time points. Oh, sorry. I'll call it our time points. I should have called it force points, but I called it force vector. It's too late. We're locked in. There's no way to change it now. Okay. I'm going to make it a black line with little X's so you can see what's going on. X label, time in seconds, and Y label, force, and it's going to be in newtons. Those are the units we're dealing with right there. Let me get that out of the way so you can see everything a little easier. Okay, let's we'll run everything over again. We're running the whole optimization, and then we'll get the plot out at the end. All right. Maybe the smart way to do it is just to make sections of code and only run a new section. So we have to run the optimization. Right now, the optimization is pretty quick, so it's not too bad. All right, so hopefully we can kind of see that. You see that there? So you can see maximum force, maximum force, maximum force, maximum force. I'll make it a little thicker so you can see it. So let's add a little line thickness. So you go into the plot, you say, hey, I want my line width to be larger. I'm going to say thickness 3. That should be easier to see. I'm going to run it all again. Be lazy. The quicker way might be just to copy and paste it. Here we go. There we go. You can see the... You have a question? You have a question? Hello? All right. So you can see bang on, bang off. We got it right, okay? And time in seconds. Awesome, right? Cool. That's the final result, right? What I want to show you is what is happening inside of the optimization. When we start running it, it says, hey, here's our initial iteration. And then it decides to change its guess and try to make it a little better. and change it again, makes it a little better, makes it a little better, makes it a little better. So what I'm going to do is I'm going to take all this plotting information, okay, and I'm going to put this plot inside of the simulation code. So anytime the optimization tries to run the simulation to see if the constraints work, okay, it's going to plot what that force vector looks like. So I'm going to copy this, take this code, copy, 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 and let's go into, we have a simulate drag race.m. Okay, let's go into that code right there. I'm pulling up the simulate drag race.m. All right, and you can see here, we have a couple of things. We have some plotting going on. All right, oh, look at this. We have a plot already in there. It should be already commented out. Let's keep that, okay? What we're going to do is we're going to plot the car's position over time and the guess of the control input that it thinks is going to be a good idea that's going to improve over time. So we're going to plot the control input. So I just pasted it in there, okay? Pasted it in, make this a little larger. All right. Okay, so we good. We still need to know, we don't have time or force points defined, so we're going to need to copy that over as well. I'm going back over to drag race. I'm going to grab my force points and time points here. Okay, I'm going to grab that, go back to drag race. Okay, I'm going to copy and paste that right before the control input. So here we have, we have everything defined. We don't have n defined, so the way to get n defined is we know that the drag race code, it just takes in the decision vector, and then it does a simulation, right? And so what it does is it pulls out, what does it pull out? It pulls out the time final, and what's it do? Okay, it sends in W. Yes. So what we're going to do in order to get n is we're going to say n is equal to the number of elements in W minus 1, right? The number of points we have is going to be the number of values we have in this thing right here, okay? But keep in mind that our decision vector also has t final at the end right there, so it's going to be 1 fewer, okay? So minus 1. There we go. So now we have n defined. That's great. There's no W star. We got to change this to W. Change that to W. And I think that should do the trick. So what this will do is this will plot these force points like this every single iteration. Okay, I'm going to set some axis limits on the plotting here because it's going to change a lot over time. I'm going to change the axis limits from horizontally from 0 to 1. What's our initial guess? Excuse me. Let me look at our initial guess for that. Our initial guess for our time is 1. Okay, great. Okay. So I'm going to say our axes are from 0 to 1. And I'll make our limits between, minus, we'll do minus 10 and 10. Those are the literal limits. It can't go any bigger than that, right? Okay. And what I want to do is I'm going to add a command that says draw now, because this plotting command is going to be called a lot. And MATLAB does a smart thing that unless you tell it to, and it's plotting a lot of things all at once, it'll wait to show them until you tell it or it's done running the code, right? But I actually want to see what happens when we have a whole bunch of plots here, when this thing changes over time. So in fact, what I'm also going to do is I'm going to say I want this always to plot on figure 1. Otherwise, I'll make a ton of figures. I don't want to do that. So, okay, figure 1. I'm going to save this. I'm going to rerun dragrace.m, and we're going to see what happens. Okay, you got that? Put that in the chat. So, okay, and I'm not sure what else you needed in the chat. Really, this is just the other stuff in the chat over there. This is from the other code. That's from the force points part. All right, now let's run drag race. Watch this. Okay. It's moving around. Watch this. This is the optimization trying different solutions. Watch this. Boom, 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 boom. Come on. Clearly, it's not the bang solution yet, but it's starting to move there. Look at this. We're watching it morph over time. It is trying things out. Okay, it's trying to minimize the cost and satisfy the constraints. You can see it's already starting to shape up a bit. It's starting to move this little higher, this a little lower. We're watching the optimization do its thing. Look at that. And you can see, look down below. This line right here, I'm not sure you can see this 10 to the minus 6th. That is saying, hey, we're actually getting pretty close. This is how close we are to, I believe, an optimum. Let's check out here. Okay, I'll wait till we'll talk until we're done. Look what's happening. Hey, we're getting closer and closer to bang. See that? Look at that. I think we're almost done. I'm looking at these two values right here. This 10 to the minus 10, 10 to the minus 5. Once this hits 10 to the minus 6 or so, we'll be done. There we go. Okay? And we are done. I don't know why it keeps popping up there. We're good. So, fantastic. Local minimum found that satisfies the constraints. Nothing changed in the optimization, only changed what we were plotting. Anyone getting that? So, you'll notice that it was trying different things. It was, and also, look at this number right here, this F count. That's how many times the functions are called. That's a function count. So what is it doing? What is the optimization doing? Okay, let's go to the board. Okay. What it is doing under the hood, my friends. So these optimizations, so the optimization algorithms these are local optimization algorithms, are evaluating the gradients of the cost and Jacobian of the constraints. These are just the derivatives. There's different words for derivatives, right? Of the constraints. To determine which direction to move W. Okay? So if you don't tell it otherwise, okay, it's going to use a method. It's called finite differencing to know those gradients. Okay? So by default, these gradients are estimated with finite differencing. Literally all that means is that if you have some function f of x and x, and you want to know what the derivative is here at x, what can you do? You could say, hey, I have some little delta x, some tiny little difference, delta x, right? And I can say, hey, what is f of x plus delta x minus f of x over delta x? That's the approximate derivative, right? So if you are at a current value, in this case of your decision vector, you then take every value in that decision vector, bump it around by a little bit, you see what happens, you divide by the difference, and you get your derivative, right? That's finite differencing. You've seen this before in the context of Euler integration, finite differencing. Finite differencing. That's some of my worst handwriting today. Differencing. Okay. What does that mean for the code? That means anytime that it wants to get the gradient or any partial derivative it wants to get, right? It has to rerun the simulation. It has to know what f of x with delta x is. It has to see what happens when you run the simulation. And if it's a cost function, did the cost function go down? if it's a constraint, that the constraint get closer to being satisfied. And so that's why you're seeing the code here execute over and over and over and over again, right? In fact, you might notice a certain number of function counts here. Right now, it's for one iteration to know which way to step your W is doing 12 function counts. Well, my friends, you'll notice that how big is our decision vector? Our decision vector, W star, has how many elements? It's got 11 elements. Okay, so what is it doing? It is running your function, your objective function and constraints for your current guess and stepping in 11 different directions. Okay, one for each decision variable. So 12 function calls, did 13 for some reason, not going to try to explain that, but you get the idea, right? So if you wanted to run a finer grid of points, right? So right now, if you look at where's our cool plot of all of our, there we go. Right now you have 1, 2, 3, 4, look at all those points there, right? If you want to do a finer grid of points instead of 10, let's say you did 15, right? Let's try running that. It might take a little bit, okay? It's going to have a lot more function calls. It's going to take longer. You can see here, I changed n to 15. That's all I did. I went into the drag race code, changed n to 15, and I'm running it. That's all I'm doing. Anyone getting this? Or are people stuck? People are getting this. Good. It's probably going to take longer to run because it has to do so many more finite differencing steps. Okay? And you can actually see this in the function count. You can see the function counts popping up right there. You see this 370, 387. So it's, there's an extra 5 or so function calls because we have 5 more decision variables, right? But at the end of the day, if this works, it should have a much more crisp, like little drop off from the bang bang controller. Okay? So you might say, wow, that means that we have to, that like if we want this to run quickly, we got to be careful how many decision variables we add to the problem, right? Because it's going to take a lot longer to run. And also, one thing that I'll point out while this is still running, I'll scroll over to here. This estimate, finite differencing, that's just an estimate. Okay? Unless delta x is infinitely small, which it can't be on a computer program, then this is going to be a guess. This is going to be a numeric estimate of the derivative, right? It's not the exact derivative. It's not like knowing that the derivative of sine of x with respect to x is cosine of x. That's exact. This is approximate. So that approximation can be just a little bit wrong, and it can be wrong enough that when you're dealing with tiny, tiny numbers, look at this down here, 10 to the minus 7, 10 to the minus 8th, it could actually get confused and not know how to solve the problem correctly. In fact, I want to see if I can get this to the point where it does not succeed, because you have not seen these optimizations fail yet, at least not in my code, but they absolutely do for all kinds of reasons. So let's start introducing you to that stuff. Hopefully we can get to multiple shootings soon. If not, we will definitely be doing next week along with direct collocation. Let's see, let's put the gas on it. I just kind of want to, it's not clear always what's the heck's going on to people in the background of these optimizations. So it's kind of just magic. Oh, look at that. Beautiful. Local minimum, it says local minimum found that satisfies the constraints, right? Took a lot more function calls. And actually, I think it took a lot more iterations. I'm not sure. I didn't check how many iterations there. Right now, there's 88. I'm not sure if you can see that. Okay. Actually, I'm not sure you can see my cursor at all. Oh, no, you can. You can see my cursor. Kind of. All right. Well, there you go. 88. I'm trying, not sure why that's not, it was going away. Okay. But you can tell that was like a little finer drop off. Let me just put this in so you can see it again here. Boom. Here we go. So you can see this, it's a faster drop off right there. Anyway, whatever. My point being is it took a lot longer. So why on earth would you add more decision variables unless you had to? Well, here's the thing. if you are performing trajectory optimizations on nonlinear. Actually, I forgot to write something in my other notes. I'm going to scroll back up real quick. Scrolling back up to the less effective on nonlinear unstable systems. Apologies. See that right there? Less effective for nonlinear unstable systems. Okay. Linear unstable systems are still pretty easy to handle for trajectory optimization. Okay. Okay. If you're performing trajectory on nonlinear dynamical systems, okay, the local derivatives can be misleading to solve the problem. Okay? And this is why we're going to, oh gosh, oh, sorry. Hey, sorry, my dog is here. Say, hey, buddy, you okay? You okay? Are you like all right here, buddy? Sorry about that. Scare you. Sorry about that. It scared me. Hey, buddy. Oh, all right. You're all right. Hang out in your dog bed. Hang out in your dog bed. Jeremy, you okay? So this is Fermi. He's named after the particle physicist Enrico Fermi. Hey, buddy. Say hello to the students. Oh, buddy. All right, let's go in your dog bed. Dog bed. All right. So, sorry, where were we? It can be misleading to solve the problem. And I'll kind of show you why. All right, let's go back to me. All right, sort of big picture. So let's take a problem such as swinging up a pendulum. Okay, again, let's just say that there is a motor here at my hand, and I want to swing it up, right? If I have all the torque that I need to swing it up, to get from bottom to top, I'm telling you about the trajectory to do that. Okay, this is pretty simple. Okay, it's a pretty, even though the dynamics are nonlinear, it's a pendulum, as we covered before. A single shooting trajectory optimization will probably solve this pretty easily, because if I have enough torque, I can swing it to straight up, stop, we're good, right? But what if I limit the amount of torque that I have available? Okay, I can only apply a little bit of torque, a twist here, right? Okay, it actually becomes what we call underactuated, because technically speaking, we lose the ability to drive the system arbitrarily in any direction. That's a better definition of underactuation, where we need this, okay? And it's nonlinear, okay? So what we can do here, so imagine now we are, so how do we get this to the top? If we only have a little bit of torque, we pump it like a swing, right? Pump, 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 pump. Inject energy till eventually, gets to the top, right? In that case, single shooting can be really misleading. So, for instance, it might say, hey, I want to swing up, and it will say, I'm going to put as much torque as I can in this direction. And it'll say, man, I really want to go further. The gradient says I should try to push it further, harder and harder and harder, but I can't. I'm limited in the amount of force that I can produce. So that gradient is misleading, okay? Whereas what we need to do is actually swing it backwards and then forwards again and backwards again and forwards again. Even though the gradient would say I need to push it that way, actually I got to go in the other direction, right? And it's hard for single shooting to see. So that's why we have these methods called multiple shooting, all right? Multiple shooting. And this is a formulation, okay? Keeping in mind, these are all using the same optimizers. The fmin_con that's optimizing the system, we're still using that. We're not changing anything about fmin_con. We're only changing how we give it the problem to solve. We gave it a single shooting, now we give it multiple shooting. So multiple shooting So multiple shooting. A multiple shooting a multiple shooting formulation adds additional decision variables which define the state trajectory. Okay? Before, we only needed the input trajectory for single shooting. We need the state trajectory. Okay? And enforce continuity via defect constraints. In essence, multiple shooting adds more decision variables and adds more constraints. Seems like a bad thing with finite differencing, but for certain systems, we need it. Okay? Sometimes it can even run faster to solve in certain cases. Okay? So what does that mean? So the idea is that before we might have, when we're defining our decision vector, W, might have a whole bunch of control inputs, U, for our U of t. Okay? Here's U of t. Here's t. Might define it as some spline over time, right? Okay? But we also, I'm gonna circle in blue all of our decision variables. Blue, 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 blue. Those are our decision variables, okay? And now, let's say we have our state trajectory over time, x of t. That's our system state, okay? And we're going to simulate for only a little bit of time, okay? Typically, we choose the exact amount of time, you put these right above each other, right? That in between are little points on our spline. Sometimes people call them knot points or spline points, okay? We only simulate for this far in time. And then we add another decision variable, okay, which is associated with our state, okay, at this time here. And that's a decision. And then we simulate again for just this amount of time. Okay? In fact, I'm going to do a whole bunch of little lines like this, right? Okay? And you do this for all, and you add a decision variable for each and every time point, but for your state. Okay? So here are your new decision variables. Boom. Sorry, wrong one. Boom, boom, boom. And for each of those decision variables, you take that state and you simulate it forward. Okay, simulate it forward. You may not need one for the very last point here. You probably don't. But along the trajectory, you have each of these little decision variables with your state. So this is your state trajectory now, right? It looks silly because it's discontinuous. Your state jumps from here to here, from there to there, and then from there to there, and then there to there. That's impossible for a continuous system. Like your pendulum's not going to teleport. Okay, it's defined by the dynamics, the physics that we've drawn, that we derived, right? So how do we make this physically possible? Well, we add a constraint, I'll do a little red line here, where we say, here's a red line here. That difference between there and there, that's the defect. Called the defect. And we want to tell that it must be 0 with a constraint. Okay. Which means that we are adding to our decision vector over here, okay, we have to add decision variables for all of our states as well. Now, I'm writing this as of t, but they will be individual variables, you know, u1, u2, u3, x1, x2, x3. for every input and for every state, okay? And we have to add more constraints. So the result of this simulation, it must end up at the state that's the same as that decision variable there, okay? Now, how and why does this work, okay? The reason that this works is because let's say we have this problem where we need to go to a system that we can't drive our state to very easily with just a guess of our control input, okay? Let's say we want our system to go up here. That's the final state that we want. But we try a guess and it goes down here and it's unstable and it can't figure out a way up, okay? Well, the gradient descent that we're trying to do with the control input might not be able to figure out a way up very easily. But we know in state space, we could say, hey, what if we told this variable just to go up, okay? And told this variable to go up. And then the optimization could say, okay, all right, let's try just moving that state up. And then we'll have this control input here try to move up and catch it, all right? It's sort of little baby steps. It'll actually have a better way of figuring it out, okay? It is actually a lot more reliable. Mathematically, why is that the case? So if you break up this big nonlinear shot, big single shot, into a tiny shot, the shorter that shot gets, those nonlinear dynamics become locally linear, right? They become locally linear, and that actually makes our gradient descent steps more accurate, okay? A lot of this I'm sort of hand-waving away, but the point is that this actually can help you solve trajectory optimization problems better, all right? So this adds, let me do a little thing. We need to add decision variables. Okay. And add what we call defect constraints. Okay. Okay, so multiple shooting is more reliable for underactuated and unstable nonlinear dynamics. Okay. The downside is we've added all of these extra decision variables, so it can take longer to solve. Okay. So let's try to take this problem that we already solved with single shooting, and turn it into a multiple shooting problem. Okay. So let's go back to our code real quick. Okay. One thing I want to do is I want to show what it looks like for the optimization to fail. Let's see if we can do that. I mean, one thing we can do is we can make it literally impossible to do. But what I'm going to go to simulate drag race. I'm going to comment out this plotting. Okay. I'm just going to comment this out, everything from the draw now, because I don't want it plotting the entire time. I'm just going to single that out. Gone. Save that. I'm going to go back to drag race. I'm going to change N to 50 and see what happens. See if it fails, because it's going to be a lot more decision variables. I want to show you what a failure looks like in the nonlinear optimization. Oh, okay. Here we go. Here we go. I changed it to 50, and it says converge to an infeasible point. Okay? It failed. That's bad. And take a look at the result that popped out. Let's see if I can find it right here. Right there. See that? Clearly not right. What happened is that it got trapped in a local minimum and trying to satisfy the constraints, and it failed. Okay, I'm going to change it to 25 and see if it still fails. Here we go. Is it going? It's going. It's going. See what happens. Change it to 25. Here we go. All right, notice it says solver stopped prematurely. Okay? You can see that it's mostly right. It's kind of sort of right, but it stopped prematurely. Why? Because there's a limit on how many iterations, how many function calls and iterations you'll allow it to do. Okay, that's so your code doesn't run forever. And the limit by default is 3,000. Okay, so you can actually change that value. So let's change that value. And you can change it in the options right here. You can say, add to your options, you can say max function evaluations. It has a little option right there, max function evaluations. And we'll put this on the next line so you can see this more easily. Max function evaluations, instead of it being 3,000, I'm going to make it 10,000. 10,000. Okay. So if I run it like that, you see it keeps running. Local, okay, fantastic. I came up with a solution. Looks like that. Notice what it says, local minimum possible. Not local minimum found, local minimum possible, right? So what does that mean? Local minimum possible says, hey, my problem, it's feasible. Meaning that this feasibility column is small enough. It's good. It's within tolerances. We can change those tolerances as well. You can quickly Google that. And however, this first order optimality, meaning are we at the bottom, the first order necessary conditions, that we are at the bottom of the cost curve, we're not sure. We're not sure we're at the bottom of the cost curve because this value, while 10 to the minus 4 is small enough, it's not infinitely small. Okay, it's not, I think 10 to the minus 6 is the default. All right, for that threshold. So that's good. That's really good. It means this is it satisfies all constraints, but it might not be perfect, right? So you'll notice that, like, if you squint, and you can't always see on my screen right there, if you squint, you'll see it's not perfectly at the top of the bang bang solution yet, right? So let's make it just 35. Just to show, I just want to show what these different kind of failures look like. All right, and some of these will be solved with multiple shooting. By the way, yeah, 35 fails horribly, right? And that's because finite differencing kind of fails it. All right. So that's what's going on. So let's make a multiple shooting version of this. Okay. So for multiple shooting, I'm going to create a new, I'm going to go back to the dragrace.m. Dragrace.m. Okay. I think can we just start from scratch here? You have to go back to the board first. So let's do our multiple shooting approach. And then in class on Tuesday, we'll cover direct collocation, which is my favorite. Okay. All right. So let's do our car, our example for our car, for our drag race. So if we're setting up our optimization problem, our formulation, we need 3 things for our optimization formulation: decision variables, cost, and constraints, right? So our decision variables, now we don't just have F1 through Fn. We're also going to need variables for all of our states, x of t. So recall that our state vector x of t for our drag race problem has our displacement s of t and s dot of t, our position and velocity. That means we're going to have s1 through sn. And we can have, we'll call it ds1 through dsn. And we also had a final time t. This is a little longer than I thought. I'm sorry. Some final time here. Okay? Where these are our velocities. Those are our positions. And these are our inputs, control inputs, right? And then it's final time. Okay. Those are our decision variables. Okay, F1, you see, because these are all our states, right? States. Along the trajectory. Okay. Good news, friends. Our cost function is still super easy. I'm so glad to report, my friends. Cost J of W is just equal to T final. We're still trying to minimize time, right? Okay. The other constraints are still the same for our constraints, but we have to add, we got to add our defect constraints. The things that make all the lines line up so it's continuous. Add our defect constraints. Okay? I'm just going to write them in terms of just math, okay, where we're going to be integrating our dynamics, right? So if we have some xk plus 1, sorry, 1 second. Give me a second. I'm going to go to a waiting screen. Pardon the interruption, folks. I'm back. Hopefully you can hear me again. Great. So, all right. All right. So we have xk plus 1. Let's say that is that's the next state in the trajectory. So if you have, state S1, that would be xk is k is equal to 1. S2 would be xk plus 1. Okay? So for a particular state, okay, must be equal to the integral. So we're going to integrate our dynamics. We're going to simulate, okay, from time tk to tk plus 1 of our dynamics or nonlinear dynamics f of x dt, where our initial conditions are, oh, sorry about that. Thank you. Apologies. There we go. That's really important. Thank you. Okay. X of xk plus 1 is equal to the integral from tk to tk plus 1 of your dynamics f of x dt, where your initial conditions are xk. So that's what we're going to have to simulate. Okay. Recall that x dot of t is equal to f of x of t u of t. Okay. So that means we're going to have to simulate those dynamics, right? So we're going to need a bunch of these added constraints that are going to pop into our problem. So let's see if we can add these constraints. So let's go. So and all the other constraints are going to be the same. Okay. So let's go back to the code here. So we have to make a new script. Okay. I'm going to make a new script entirely. I'm going to call it drag race multi.m, written by me and all my friends here in 2026 02 26 common era. See, we're going to clear everything. CLC clear, close all. Okay. All right. And so I'm going to save it as drag race multi. Okay. All right. A lot of this stuff is going to be the same. So we're going to need to be able to, okay, what are we going to need? We're going to need a cost. So we're going to define our cost function. Okay. We'll also define our number of spline points. We'll call it n. We'll just say n equals 10 for now. Okay. We're going to try to solve the drag race problem using multiple shooting. Okay. And our cost function, we call it cost, is going to be an inline function. So we say at w takes in w, and then whatever the last value is of W, your decision vector, right? That's going to be your final time because we're minimizing time. Same as last. Same as the last version, okay? All right. Okay, so we have our cost function. Easy. Now, look at our decision vector, okay? So how many, if we have n, if n equals 10, how many decision variables are we going to have for this formulation? Count them up, friends. Anyone want to guess in the chat here? If we need them for our control inputs, which we have 10. We have for our first state, S1, we have another 10. We have another 10 for DS. It's another 10. And then 1 at the end for your final time. So we have 3n plus 1. Exactly, Marco. So a 31 in this case. So we're going to have 31 decision variables. So our cost function is easy. Our constraints are going to be harder. So let's go look at our, we had our nonlinear constraints drag race function. Let's take a look at what that was. I'm going to open up our nonlinear constraints drag race, okay? It required us simulating our drag race, okay, each time to know what the final position was, okay? The only thing that changed, one of the primary things that changes here is that we're not going to be simulating across the entire trajectory. That's multiple shooting. There's single shooting, okay? We're going to want to do multiple shooting, so lots of little shots. So what I'm going to do is I'm going to create a new nonlinear constraint function. And get rid of the other things. We don't need that. Don't need that. Only thing open now is drag race multi, our new function we just made. We're going to make a new function, okay? Okay. I'm going to call it non-lcon multi, okay? .m. It's going to be a function, and if it's a nonlinear constraint, you have to return your inequality nonlinear constraints and your equality nonlinear constraints. I think we call them G and GEQ for our problem. Is equal to non-lcon multi. And it has to take in our decision vector. Okay? I'm going to save it, non-lcon multi. Okay. What's going on here? All right. I'm going to compare it to our previous non-lcon drag race. I'm going to pull that up so I can look at it. Yes, we had no nonlinear inequality constraints. We had a final position. Yes. Okay, that's what we're going to have. So we're going to grab these two lines from non-lcon drag race and copy them because they're going to be the same. Okay. We're going to set S final equal to 1 as a final position. We have no nonlinear inequality constraints. We only have nonlinear equality constraints. Okay. These defect constraints, they are equality constraints because they're saying that the difference between this, the next state in your decision vector here and the result of the simulation has to be 0. Okay? All right. So here's our old nonlinear constraints where we just run a single simulation of drag race. We need to do multiple simulations of drag race. So what I'm going to do, my friends, is I'm going to make a new version of our simulation code. So I'm going to pull open simulate drag race. I'll make a new version of it. This is simulate drag race. Okay. I'm going to call it simulate multi. Okay. And I'm going to save as simulate multi. It changes the name. It's now called simulate multi. There's a new copy of the code. Okay. The only thing I want to change is instead of sending in just the decision vector, I also want to send in the time span. Okay. I want to send in the time span. Right now, we are grabbing the time span as being from 0 to the final time. One single shot along the entire trajectory, a single shot. We don't want that. We want a multi-shot, right? So we're going to have simulate multi send in the time span. Okay? And we have to send in the initial state. Okay? Keeping in mind that we're now going to be simulating starting different initial states. We might be simulating from there to there, then start at this initial state, go from there to there. So we have to tell it what the initial state is. It might not be the starting point for the race. In fact, it will not be many times. So we're going to put in the code here, x0 and time span. So this initial state here, we're no longer starting at the start of the race necessarily. Gone. Okay. Heck, we're not even using TF. I don't think. Are we using that? Yeah, no, we're good. We're good. Yeah, we're going to keep TF there for reasons. Okay. All right. So, we should be good there. Should be good there. Okay, x0. Cool. So we have to run a simulation, but we have to tell it what the initial state is for the simulation and how long we're and the range of time we're simulating it for. And when we are done, it will just tell us, yeah, it'll just return the final position and the final velocity, the two states. It's exactly what we want. Exactly what we want. Okay. So now let's go back to non-Elcon drag race. Okay. Oh, sorry, non-Elcon multi. Okay. Now, instead of running a single simulation, we're running multi-simulation. So I'm going to grab this line at the top of simulate multi, put it in non-Elcon multi. Cool. And we're going to take a bunch of shots. Not literally. I mean, we're going to take, we're not counting shots. Okay, but we're going to take do a bunch of little simulations. How many are we going to do? If we have if n is equal to 1, 2, 3, 4, 5, say 6, right? We're only going to take 1, 2, 3, 4, 5 shots, or n minus 1 shots. So we need to know how many shots we're taking, number one. So to know that, we would say that, hey, n is equal to the number of elements in our decision vector w. Okay? Before we would say minus 1, but we have so many more decision variables now, right? Right now we have 31 because we have 10. So if you want to calculate that, what we would say is we would subtract 1 and then divide by 3, right? Because we have now not just one control input, we have now 2 states added in. So that should tell us the number of shots that we have, and then we subtract 1 again. Sorry, it's a little bit confusing as to what that is. But basically, if I have 31, okay, 31 minus 1 is 30. Divided by 3 is 10. So that means we would have 10 points, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. But then we actually shots in the middle. We only have 9 connecting points. It's called a fence post problem, where if you have 10 fence posts, there's only 9 connectors between the fence posts. So that's the minus 1. We'll call that n shots. N shots is equal to that minus 1. Actually, here's what we'll say. We'll say n is equal to that. This is the number of spline points. And then n shots is equal to n minus 1. So we always have 1 fewer shot than points. Okay. All right. So now if we want to do all the different shots and add defect constraints, what we're going to say is we want to loop this and say, hey, for iter is equal to 1 colon n shots. We want to take n different shots, right? We are going to run a simulation starting at some x0, which is our current initial state. So if we're on shot 1, it's that one. If we're on shot 2, it's that one. Okay? And for a certain time span there. Do we need t-final? Yes. So we do need to know what t-final is, I think. So let's say t-final. T-final is equal to w end. We're going to have to end soon. I apologize. We're going a little bit over here. Maybe what we'll do is we'll finish this up in lecture on Tuesday. We'll be in person, but I'll set up my computer with the code so we can do it in person. It's not ideal, but this takes a little longer than it takes than I expect sometimes. So that's the final time. Let's just get this loop together and start with this. And so we need to loop through a bunch of different shots, and we're running out of time here. We're basically done. So in which case, we're going to loop starting at the first shot, and we're going to say, hey, it ended up there. How does that compare to our next decision variable? And then we subtract them because when they're equal to 0, it's solved, right? Okay. So let's stop there for the moment. Copy this into the chat before we go. And happy to stick around for a minute or two. But thank you all for coming by. All right, so we'll finish up on Tuesday here.